Okay, good morning. I guess as a bit of a debrief from yesterday, Alex, I think you said you were at about 6% or 5 point something percent error for your total average compared to the speed of sound calculated from the temperature on the thermostat. What were some other, is that pretty much what everybody got? I mean, in theory, we all had the same data, so you should have been getting around, what was it then? 5.2? Was it positive 5.2 or negative?
Negative.
It was negative. So we were a little bit lower. And can I ask you a question? I don't know, you'd have to look at your data, but were you consistently lower, or were some of your speeds higher and some lower and it averaged out lower, or were they all lower? They were all lower. So, you know what I would probably say to you then is that if all of our results were lower than the number we got from the thermostat, I would probably say maybe the thermostat is reading too high of a temperature. So I don't know what it said yesterday. It says 21.0. Does anybody remember the temperature it said yesterday? 21.3. So maybe, and you use that 21.3 to calculate the speed of sound, maybe it was actually only 21.1. And if you use 21.1, that would bring down the speed. I'm not trying to suggest we should look for a way to repeat the experiment and get better results. I'm trying to come up with a reason why our results are consistently lower. And, you know, that theoretical value, so when you use 21.3, what'd you get for the speed of sound?
343.78.
343.78. So, you know, ultimately that speed of sound of 343.78 is not a theoretical speed of sound because it's based on a measurement that the thermostat is making. But you are expected to know the relationship there. So on an exam, I might tell you that a student does a similar experiment and they hear a constructive resonant noise when there's 32 centimeters of air in the tube. Calculate the speed of sound from that number, and also from the frequency on the tuning fork. Or I could give you a situation where I give you the frequency of the tuning fork, I give you the temperature of the air, and I say, what should the shortest column of air be that will produce that constructive tone? Which would mean you'd have to work on finding the speed, so you could find the wavelength, so you could divide that by 4. Okay, let's take a look at the handout that I've given you here. This is, I have a feeling I've got an extra number in my lessons. I think I skipped 7 or 8 or something. I don't know. Don't worry about looking back. But anyway, I've numbered this lesson 10. I've numbered this lesson 10, and this is called diffraction and interference. In this course, you are expected to be able to explain diffraction of waves and also explain or state when diffraction happens. In this course, you have to be able to use the superposition principle of waves to determine the properties of two waves that combine. And when two waves combine, that's called interference. In this course, you are expected to explain constructive and destructive interference of waves. But in this course, you are not expected to be able to use Young's interference formulas to solve problems, even though we're going to do it today. The reason we're doing it is it's something very closely related to diffraction and interference that we study in Physics 30. And Physics 30 students struggle with Young's double slit formulas. So they're not complicated formulas, but for some reason, it's a struggle for some students. And I feel as though if I can give you a little bit of a leg up on that by doing some problems with you today, then next year when you're in Physics 30, you'll go, oh, I remember this. And by the way, we're going to learn this thin layer of those formulas. In Physics 30, I'll be teaching those formulas and then building on them. There's a lot more. I'm not teaching you everything you would learn in Physics 30. I'm teaching you just an introduction. So let's start off with what diffraction is. First of all, diffraction is something only waves do. Interference is something only waves do. This becomes crucial in understanding how energy is transferred from one point to another. because energy can be transferred from one point to another using particles or using waves. If that energy is capable of being diffracted, then it has to be a wave. If that energy is capable of being interfered with by other forms of energy, I want to be careful with that. Let me back up. If that form of energy is capable of interference, then it must be a wave. Particles do not interfere, particles do not diffract. So first of all, let's take a look at what diffraction is. Diffraction is when a wave passes through an opening, it spreads out. So what we're looking at in this diagram is a series of ripples, say in water, that are traveling in the direction of that red arrow, and on the other side, they spread out. What does this mean? It means, imagine that there's a beach over here, and they put these two concrete walls in here to maybe reduce the amount of erosion on the beachfront property, or maybe there's just a lot of waves coming in and it's too dangerous for people to be out in the water next to the beach. So what does it mean to say that this water diffracts, or this water wave diffracts? What it means is that if I am sitting on my little floating mattress here, doesn't matter where I am, I'll say I'm here. There we go. And I've got my sunglasses on, I have my book, I got my pina colada, my tropical hat, and I'm just sitting there enjoying the day. It means that when these waves go through this opening, even though I'm behind a barrier, I will still be bobbing up and down. That's what it means. It means that some of that wave energy doesn't continue to go straight, some of it goes in this direction. Some of the wave energy goes in this direction. Some of the wave energy continues straight, some of it goes in this direction, some of it goes in this direction. So I can't hide from the wave by sitting there. On the other hand, if we had a barrier like this, and I'll have to draw one, if we had a barrier like that, and you were playing paintball, and I stood there, and you stood over here and fired paintball pellets through there, I would be safe. Now, you know, I don't want to discount the idea that maybe a paintball could somehow bounce before it breaks off of this edge and hit me. That's not what we're talking about, though, right? Particles don't diffract. When I stand out in the hallway, if I had a bunch of ping pong balls and I threw them through this doorway, they're going to land over here, right? Some of them are not going to go this way. But with a wave, and this is what's really important, the wave is spreading out. Some of the wave energy goes here, some goes here, some goes here, and some goes here. So a bit of terminology here. It says label the wave rays and the wave fronts in the diagram. Let me go back to the beginning here. These are called wave fronts. All of these lines, I'm not going to draw arrows to all of them, but all of these lines are called wave fronts. They're ripples. And when you see those lines, everybody, and I'm just going to talk about the lines that are in blue on the left before the barrier, this is what those lines are. And you know, you've seen water waves in a tank before, whether it's a tank of water in your house or a pool or a lake, and you can see lines, right? It's because of the reflective nature of light reflecting off of the surface, and it reflects off in a different direction at the top than it does at the bottom. So you tend to see bright lines where the top of the wave is and dark lines in the middle. Sometimes when we draw these, we will put dotted lines in between the wave fronts. And if the wave fronts are meant to be crests, then the dotted lines would have to correspond to troughs. Of course, in everything I do here in explaining interference and diffraction and pretty much everything with waves, I tend to talk about transverse waves and not longitudinal. Because we don't see ripples in longitudinal wave. You see compressions. And it's easier for us to wrap our head around ripples than it is compressions. So that's what we're talking about. Now, I do want to point something out to you. Oh, sorry, wave rays. Wave rays are simply lines that show the direction the wave is traveling. And I could draw an infinite number of wave rays here. Right? If I said, which direction is the wave traveling at this point? Well, it's traveling that way. Which way is it traveling here? It's traveling that way. Here it's traveling that way. And the number of lines that I draw is really arbitrary. I could just continue to add wave rays to this diagram all day. So the wave fronts are showing us where the ripples are, and the wave rays are showing us the direction that the light is traveling in. We tend to use wave rays because when we in Physics 30 talk about light waves, you can see a laser light under the right circumstances, but you cannot see the ripples in light. Right? If I shine laser light through a cloudy room, you'll see a line of light. You see the ray of light, but you don't see the individual ripples. I want to point something out to you, though, that the amount of, and you can choose to add to your notes or not. I don't care. That's up to you. But the amount of wave energy that's going through this opening is this narrow slice of wave energy, isn't it? But yet, some of that energy is over here, some is over here, some is over here. I've already told you that if I'm sitting on my mattress in this position, my mattress is going to be affected by the wave because the wave spread out to that point. If I'm sitting here, it's going to be affected here, it's going to be affected here. Any place in here, there is wave energy. But just hang on a second. That means the wave energy, when it spreads out, and this is what spreads out means, is diluted. Okay? If I take, I could use paint as an example. If I take a bucket of paint, not a bucket, half a bucket of paint and dump it right here on the floor under this desk, I'm going to get a lot of paint in that area, right? But if I have a paint roller and I spread it out throughout the whole room is going to be painted on the floor, but it will be spread out more. There will be less paint in different places. However, it's not spread out evenly like paint. What you would discover is that if you were here, the mattress would be bobbing up and down with a lot of energy compared to if you were here. So most of the energy is in the middle, and it spreads out, and it's diluted. So this is what this diagram would look like. If you were to draw an energy diagram as a function of the position, it would look something like that. And that's not perfect. Let me give you something a little better to look at. It would look something like this, all right? Where most of the energy would be directly across from the opening, and as soon as you moved a little bit away from it, there would be less energy, and the further away you got, there would be less energy. So if I wanted to be someplace where I could just be rocked to sleep by the wave, just a gentle rocking, I would probably want to be either far to the left or far to the right. There's clearly a limit here. You will notice that there's kind of a region here and a region here where the waves don't reach. and that will pretty much always be the case. It's not like these ripples are going to extend right to the wall. In terms of water waves, I can explain why this happens, because when the water waves make contact with these two physical barriers, the water has something called adhesion. You know, if I come in out of the rain and I step inside, all of the water that's on my face and glasses doesn't immediately fall to the floor. It sticks. So what happens as that wave front goes through the opening, the edge of the wave front sticks on one side to the barrier, and on the other side the edge sticks. So it kind of, that's why it spreads out. It actually has a name called Huygens principle. I don't care about you knowing that name. Your textbook talks about it. If you did this with particles, and this can be ping pong balls, or this can be anything you want, you're going to get an energy distribution that pretty much looks like this. Well, depends on how big the opening is, right? You're going to have a lump of energy, though. You're not going to have this distribution of energy. This is a photo taken from a Google Earth satellite image. You can see that the two reefs here are acting as an opening, and you can see the curvature of the waves on the other side. You can also see some curvature here. And in Physics 30, we will talk in more detail, but diffraction doesn't just occur by passing through an opening. It occurs when you pass close to an edge of an opening or the edge of a barrier. This is a better one, and I really like this because it illustrates, everybody, let me turn this upside down. This illustrates, I don't know what the yellow lines are, this idea that the energy peaks here. Because if you take a look at the water, it's whiter there. Waves crash. You don't understand what wave crashing means? It falls apart. When you get a certain wave of water, you get that white foamy water being created at the top because the wave is losing its shape and it's falling apart, basically. And it's going to lose its shape and fall apart if there's more energy. And there's certainly more energy here than there is, say, over here. In fact, this, can you see that wave there? But it's pretty faint, isn't it? Which means that would be where your mattress would be bobbing up and down, just a little bit. All right, there's a rule for diffraction. And this is a very important rule. Diffraction is only going to happen if the size of the opening is smaller than the wavelength, or the same size, roughly. The size of the opening must be about the same size or smaller than the wavelength. If diffraction does happen, because the opening is smaller than the wavelength, then if we make the opening even smaller, more diffraction will occur. So I'll write this, I'll show you what you can write in a second if you want, but I want to explain this in words first. As long as the opening is smaller than the wavelength, diffraction will happen. If the difference between how big the opening is and the wavelength, if that's even bigger, more diffraction occurs. So in relation to the size of the opening, the smaller the opening is in relation to the wavelength, I should say, the smaller the opening is in relation to the wavelength, the greater the diffraction will occur. And I'm trying to give you, again, a heads up here, a head start, I guess, for Physics 30, because in Physics 30, we're going to be racing through all of this plus more. And if you've seen it before, then hopefully you'll be better off. So the opening has to be the same size or smaller than the wavelength, and the greater the difference between those two, the more diffraction will occur. What do I mean by the greater the diffraction effects? Well, it means, this is going to be a little strange to think about, but it means that the wave spreads out even more. What does that mean? Well, let's imagine, first of all, that I have 3 different waves, and this one that I've got with violet color is a small wavelength, and then green is a bigger wavelength, and red is a longer wavelength. These are water waves or whatever waves you want them to be. And this opening that I've got here is smaller than all of those wavelengths, which means all 3 of these waves will diffract. But because the wavelength of this red lambda is so much bigger, it's the one where you will have the most diffraction. So the size of this opening is even smaller in relation to this wavelength than the size of this opening is in relation to this wavelength. So all 3 waves going through the same size opening will result in different amounts of diffraction. And for any of these that I put up that are not in your notes, if you want to have your phone at the ready and just take a picture, you certainly can. I don't mind that. And just leave your phone out if you're doing that, because there will be more. I'm also recording this so you could watch the video again later. On the other hand, if I had this, let's imagine I have 3 waves and they're all identical. And that opening at the top is smaller than the wavelength. Well, then diffraction is going to occur. If I make that opening smaller, then more diffraction will occur, because the opening now here in relation to this wavelength is even smaller than the opening here in relation to that wavelength. And the tiniest opening would be the most diffraction. Now, what does that mean? What does this actually mean to say more diffraction happens? Well, diffraction is the spreading out of the wave. So if the wave spreads out more, let's take a look at this distribution of energy. Very large opening, but the opening is still smaller than the wavelength. Okay? What happens if I go to an opening that's smaller? If I go to an opening that's smaller, there will be more diffraction. What will it look like if there's more diffraction? What will that energy graph look like if it diffracts more? Yep. Yeah, it'll be flatter. Most of the energy right now is in the middle, which will always be the case. There'll be more energy in the middle than there is on the left or the right. But if I make the opening smaller, even more of that central energy will be bled out to the left and the right. So this would be a medium opening, a smaller opening than the large opening, more diffraction. This would be a tiny opening where you would have lots of diffraction. And what people tend to think is they get it backwards. They think more diffraction, you get a taller graph. But you don't. You get a shorter graph because the energy is spread out more. All right, interference of waves. When 2 waves encounter each other, and we're still in the Physics 20 realm here. There's nothing I've done so far that could not be on an exam in this course. Anything we've covered could be. When 2 waves encounter each other, they have the ability to overlap or pass through each other. This is the principle of interference. Waves can pass through each other. I have probably said before, particles cannot pass through each other. That's why we have collision insurance on vehicles, right? Okay. So while the waves are on top of each other, we use something called the principle of superposition. And it basically says, everybody, that if you have, I'm just going to jump ahead here, that if you have these two waves, and the green wave is maybe traveling to the left, and the red wave is maybe traveling to the right, but this is a snapshot in time where they are passing through each other, and they're at this point. The principle of superposition says that when they're in this state, they behave together like that. They superimpose, because, I mean, think about this for a second. If you have a water wave traveling in one direction and a water wave traveling in the other, when they're on top of each other, you can't see both waves, can you? They're going to do something to the water to create a wave in the water. Well, this blue wave will be the result of them combining. This is the principle of superposition. So that if this distance were 120 millimeters, and this distance were 125 millimeters, then we would create a wave with an amplitude of 245 millimeters. They add together. Because the red wave right now is pushing the water up, and the green wave is pushing the water up, they're working together. On the other hand, if I had these two waves meeting, at this point in time, this is their arrangement, then the red wave in this region on the left of the diagram is pushing the water up. The green wave on its own would be pushing the water down. What's going to happen here? Any ideas? Jay? Will it be entirely level?
It depends if one is stronger.
What do you think, looking at how I drew that?
I think it'll go up because red is...
Right. The red has a bigger amplitude, so the blue wave will probably look something like that. I don't know why it looks fuzzy the way it is, but you know, if the red wave had an amplitude of 10 centimeters and the green had an amplitude of 4 centimeters, then the blue would have an amplitude of 6. Doesn't look quite to scale. Let me repeat that. If the red was 10 and the green was 6, the blue would be 4. That looks a little better. Okay. I want to show something to you now. We'll get back to your handout and your notes in a second. I'm going to show you a video clip of two waves passing through each other. It's very hard to reproduce. This is an old video done in a university somewhere. It's a little bit of a shabby video in terms of quality. When I say it's old, I mean it's old, like, I don't know, 1970s maybe. What you're going to see is a ripple on this slinky coming in from the right, and it's going to be traveling to the left. You're going to see a ripple on this slinky from the left coming in, and it's going to be traveling to the right, and they're going to pass through each other. Now, I know what many of you will say. I've got it on repeat, so it's just going to repeat. That it doesn't look like they're passing through each other. It looks like they're bouncing off of each other. Would you agree? That's the illusion. I am truly amazed by this, though. If I stop this right here, can you see that the one on the right that is traveling to the left is a little bit taller than the other one? It has a greater amplitude. Look at the one on the left now. It has a greater amplitude. How the physics and the forces accomplish that, I don't know. I can't explain it. I really can't. But it is definite physical evidence that these two waves pass through each other. The bigger wave is on the other side. I'm going to let it run again and point something else out to you, and then we'll get back to your notes for this part. If I were to look at the height of each of those waves, and then stop this when they are right on top of each other, that height is greater. Now, you don't really have anything to compare it to, but I believe I have captured it up here. I don't know. I think, yep. So there's an image on the left of those two waves and then an image on the right of the two waves together. And if you take a look at those heights, that height on the right is a little bit bigger than the one on the left initially. And if you add those two heights on the left together, you get pretty close to the one on the right. It's not perfect. I think part of the slinky is moving elsewhere, taking away some of the energy. But it's pretty darn close. So that, what I've just shown you, is called waves meeting in phase. When waves meet so that they act together to increase the amplitude, they are meeting in phase. So how does that happen? You have to have the waves meet crest to crest or trough to trough. Okay? Now, if it's a sound wave, they have to meet compression to compression or rarefaction to rarefaction. But it's easier to just talk about transverse waves. What will happen when waves meet in phase is the wave energy adds up temporarily, because you saw in that video that it springs back to where it was before. Adds up temporarily, and that's called constructive interference. And then on the right side at the bottom of this handout, I think you could probably guess at what we're going to say here for out of phase. And I don't know, like, to you, doesn't it make sense that in phase describes what this looks like? They're in sync. Out of phase is going to be that. And if you look at this red wave, the crest of the red wave on the left is meeting the trough of the green wave. And on the right, the crest of the green is meeting the trough of the red. So for out of phase, they meet crest to trough. Or if you had sound waves, it would be compression to rarefaction. This results in the energy temporarily diminishing, but it's the wave energy that diminishes. The energy goes someplace temporarily. And I'm going to show you a video now of this type of interaction. So we have a tall wave coming in from the right that has an amplitude in a positive direction. We have a wave pulse on the left coming in towards it with a negative amplitude. I just want us to focus on afterwards. Let's not focus on in between where they're overlapping. So that amplitude on the left now is basically the same as the amplitude it had on the right before it passed through the little guy. There's been some loss of energy due to friction, okay? But that means that if the energy comes back, but it's diminished in the middle, it must be stored someplace. It's stored as potential energy of the spring. And it would be stored as gravitational potential energy of a water wave, or different things like that. I'm going to try to pause this now when they're on top of each other, which is a difficult task. They are starting to come together here. And I've just passed it. I know I've passed it because can you see the little guy leaking out here? Okay. But you can see that the overall amplitude there is less than either of the amplitudes. Just let it run a couple more times. And let's finish off the note portion of this with out of phase. This is called destructive interference. Now, I don't know if you noticed, but on that page where I have the video links, there's a third video. The very first one that I showed you had in phase, and it was intended to be filmed so that those two amplitudes were the same, but one was a little bit higher. this next video is definitely different amplitudes. Like, there's no doubt about it. Tiny guy coming in from the left, big one coming in from the right. Afterwards, the big one is still moving to the left. And again, the physics of what's going on here is pretty weird in my mind. I'm going to try to pause it here. That's, I think, where they're right on top of each other. Would you agree? Is my finger at that height? Pretty close? Okay, I'm going to pause it here. Is my finger at that height, or is it a little higher right now? Is my finger higher? It's a little higher. That's because they haven't added together yet, but then that's going to start going up to a higher point, and then it diminishes back down to the original two waves. It's really kind of interesting, I think. Any questions about constructive or destructive interference? Okay, so we've learned about diffraction. By the way, one of the reasons why you can still all hear me in the room when I'm standing out here talking, I mean, the people who can see me, you're talking, you're hearing me because my voice is going right towards you. But the people on the left-hand side of the room can't see me, and that means, unless you're seeing me in the reflection here, that means that those people are hearing my sound because the sound goes through this opening and spreads out. You're also hearing because of some reflection. And by the way, that's also why you can hear me when I don't face you. I don't have to point my mouth at you when I talk because the sound, when it leaves my mouth, spreads out. All right, now we're going to talk about diffraction and interference of light. And we're taking a huge leap here from talking about water waves and mechanical waves to light waves, which is going to lead us into Physics 30. Remember, in order for a wave to undergo diffraction, the opening must be about the same size or smaller. Well, it turns out when you pass light through small enough openings, it spreads out. And we have with us, we carry around with us an apparatus that we can test this with right now. If you look at me or any object in the room, hopefully you're not seeing a fuzzy image. I mean, if you are, maybe you need to get a new prescription for your glasses, or you need to get glasses. But I want you to focus on something in the room and notice how clear it is. And I probably need new glasses. Things are not perfectly clear, but I can find things that are clear. And imagine that you squint your eyes now, and you squint your eyes, and less light is getting into your eyes, of course, but things should get fuzzy, shouldn't they? I hope. If when you squint your eyes, things are clearer, definitely need to go see an eye doctor, okay? But things get fuzzy. And what's happening there is your eyelashes are coming together and they're forming very, very tiny openings that the light is traveling through. And that light, which has been traveling in a crystal clear straight line to the back of your eyeball now, spreads out. And instead of getting that well-defined set of light beams hitting the back of your eyeball where your brain says, oh, that's a calculator, if your eyes are really squinted a lot, you go, oh, there's some blob there, because it's fuzzy. So light does undergo diffraction. Now let's go back to water waves. When I pass water waves through an opening, I get those circular ripples. You with me? If I were to pass water waves through two openings, I'd get two sets of ripples. Okay? Remember that those green lines are crests. And I'm going to highlight something here so that you can see this. This is in your note package, but I want to highlight this. That this opening here is what is producing these ripples. Would you agree? I'll do just a couple more. I guess I might as well do them all. Well, I'll do a couple more. However, this opening is producing these ripples. Now, I don't think there's any way for you to really add this to your notes. This is just you're sitting back and thinking about this and learning. We're producing these ripples. We'll do one more. And those ripples or wave fronts are crests. Remember I said those lines are crests. And what that means is that in a place like this, or this, or this, or a place like this, this, these are all places where crests are meeting crests, which is constructive interference. And what that means, it's a little bit weird to think about, but for a water wave, that means that along this line here, you're going to have constructive interference. And what that means is the water will be moving up and down a lot. Big amplitude, little amplitude, big amplitude, little amplitude. And by the way, it's happening here as well because that's a trough meeting a trough. I'm going to use a different color now. I'm just going to go with red to point out something to you, that you're going to have a line of constructive interference here. You're going to have a line of constructive interference there. You will have one here. You will have one here. You will have one here. You with me still? Yes? Okay. What does that, oh, I missed one. You'll have one here. And did I miss one over here? You'll have one here. What does this mean? It means that if this were water, not really happy with that part. If this were water, and I was in a boat traveling this way, I would go through portions where the boat is going up and down a lot, and then it's going up and down very little, and then it's going up and down a lot, then very little, a lot, etc. What you're going to find is that you get a distribution of energy that looks something like this on both sides. And tomorrow when you come in, I'm going to have set up at the back of the room, and I have to fine-tune it, 2 speakers set a certain distance apart. This will be speaker 1, this will be speaker 2, and they are going to, when I turn them on, make what you might describe as a very annoying high-pitched sound. And they're going to be at the back of the room. And if you stand on one side of the room and walk, the volume will go up, and then it will go down, and then it will go up, and then it will go down. And you'll actually be able to, you have to block off one ear to make this work really well. You'll be able to find spots in the room where you can't hear it. And it'll be loud. But you'll be able to find a spot in the room where you can't hear it, because you will be finding a spot like this one where the crest of one sound wave is meeting the trough of another. Now, it's not a crest and a trough, it's a compression and a rarefaction, but the same principle applies. And this is what we call an interference pattern. So I'm going to pause there. Does anybody have any questions about the fact that you would get a lot of energy, a lot of energy, little energy, a lot of energy, little energy, etc.? Any questions about that? Okay. So, I do want to show this to you. It's a little bit hard on the eyes, but there we go. Those are the waves moving, and they're spreading out. But notice that what you have, and if you're looking on video, you can't see what I'm doing here, but what you have about here is a line of a lot of energy because those crests are on top of crests from each of them. And you have another line with a lot of energy there. And you have one with a lot of energy there and one there. If, everybody, I make the opening smaller, then the diffraction is greater. And look at this. Now you have a big angle here between that middle energy and this one. If I make this opening very big and I make the wavelength very small, we get this kind of thing. And now it's starting to, could hypnotize you with this, I think. I have, actually. You won't believe me, but you've been staring at this for 10 minutes now. I'm just kidding. It's been 2 minutes. You can see all of those lines of construction. And strangely enough, do you see when you look over here, or when you look from an angle anyway, you see those kind of white spaces? Those white lines, that space of whiteness? That's actually constructive interference. If I were to take a look at, did it start again on its own? Wow, okay. If I were to take a look at, I will pause it at the right time. If I were to take a look, I don't know if I can, there it is. Here, this whole line is constructive interference. So that means over here, you're going to get a lot of energy here. This whole line is constructive interference. You get a lot of energy there, but you get more energy there, don't you? Am I going to get a lot of energy here? Yep. But less than I do at the one below it. Am I going to get a lot of energy here? Yep. I will get even less here. Do you get the idea? Okay. All right, back to the note package. Well, it turns out that that's what happens with light. So when you shine a beam of light through an object that has tiny openings in it, 2 tiny openings, you don't just get 2 beams of light. You get what we are looking at here on the right-hand side of that screen. And I'm going to show that to you right now. So I have a number of lasers. I have a green laser. I have a red, this is a green one too as well, yeah. I have a red laser. And I have the very valuable and very rare violet laser. I'm just kidding, it's $10, okay? But most people see red lasers. You don't see green lasers being used for presentations because, quite frankly, that's bright. Like if you were looking at that a lot, it's quite bright. It's hard on the eyes. And depending on how charged the battery is, it might be even brighter. Like that's pretty bright. Okay. And they're fun to play with. But I have here a, this is the physics 30 part that I don't want to get into. This is called the diffraction grating, but it has openings in it. Okay? It has 2 openings. It has more than 2 openings, but just think of it as having 2 openings because it turns out that this thing we're looking at here, this thing that we're looking at here is going to happen even if we had these 2 openings and there are just more and more openings on top of each other. Okay? I could have 100 openings next to each other. You're going to get the same pattern because what's happening with these 2 openings, if I had another opening here, what's happening with these 2 openings is the same thing as what's happening with these 2. And it's going to happen if the openings are equally spaced. Everything is going to be piled up nicely. Sorry, not piled up nicely, but everything is going to be matching up. If I take this whole pattern and I move it up or down a certain space, I'm going to get the same result. Okay? So when I shine white light, sorry, not white light, green light through here, I get that. And if I wanted to, I could turn on a fog machine in the room and get some fog going, and you would see, by the way, that there's actually beams of light from here to the ceiling, right? In fact, Alex can do me a favor and just put your hand, just take your hand slowly, and you're going to move it across this way, just even your 2 fingers, okay? When I say go. Okay, go ahead. So he blocked out that one. Keep going. He blocked out the middle one. He blocked out the top one. There's actually beams of light, but you can't see them. Okay? If I fogged up the room, you would see them like you would see headlights on a foggy day. So that's green. If I go to red, and red has, by the way, a longer wavelength, which means the difference between the size of this opening and the wavelength will be more. These are further apart, aren't they? If I go to violet, let's go back to green. And I'm going to say that the distance between that center dot and the next one is 80% of a tile. By the way, you notice the green dot in the middle is brighter? Less energy on both sides. Now if I go to a violet, now a violet laser has a shorter wavelength, so the size difference between the opening and the wave is going to be smaller, which means these points should be closer together, and they are. If I go to a different diffraction grating, and we'll go back to the middle one, which is green, I see more dots. I may have to change lasers here. I see more dots. Right? I see a total of 5. Yes? My laser is dying, but do you notice that the dot in the middle is the brightest? The 2 next to it are dimmer, and then the further 2 are even dimmer. Well, if I go to red now, well, it should be further apart. I don't see a 4th and a 5th one. You're not always going to see 5 dots. If I go to violet, the dots are very close together, and I can see, how many of you can see a 4th and 5th one? It's very dim, isn't it? This color is weird. Let's go now to different diffraction gratings other than those. And I'm going to start with the violet. And we'll kill the lights to make it a little easier. So there's my violet light. I'm going to go with openings that are a certain size. You see quite a few dots, don't you? Smaller opening, even smaller opening. Green opening is small enough. Smaller opening, even smaller opening. And then red opening is small enough to cause it to happen. Opening is even smaller. Again, smaller the opening, the more diffraction occurs, which means things are spread out more. All right, we're going to do a few examples now just to explore formulas that you're going to be using in Physics 30. You will need to turn the page. I've explained all of this. And at the top of the next page it gives you these 2 formulas. Everything you have seen and learned up to this point is fair game. The formulas are not for exams. So we're going to do some of these together. You can maybe try a few on your own, but you don't have homework. We have these 2 formulas which relate the wavelength of the light and the properties of those dots, where those dots are, how far apart they are, all of that information. And I hope you would agree, I don't know, to me it's obvious, but just because something is obvious to one person doesn't mean it's obvious to other people. If I take a look at the distance between these red dots here, you see it? What do you notice happens to the distance between the dots if I get closer? Well, the dots get closer together. There's some relationship between how far apart the image is compared to the openings, and how far apart the images are in the collective image. I hope you agree that when I change the size of the openings, that the dots' distances, the spacing changes. There's got to be some relationship between that. I hope you would agree that when I change from red, which has a certain wavelength, to violet, which has a different wavelength, the spacing changes. All of this stuff is mathematically connected, and this is the formula that we use. Lambda equals xd over nl, or lambda equals d sine theta over n. Because I know I have some students in this class that are very strong, and they might discover something by thinking about these formulas in a minute, I want to point out something to you. That this formula on the right is a valid formula that works 100% of the time. The formula on the left doesn't work all the time. They're different, they're not compatible with each other. In every question we do, this formula will work. There's a set of circumstances that this formula works in, and there's a set where it doesn't work. That's a Physics 30 idea. But you need to now add some things to your diagram so you know what all of these variables are. So what we have here is the screen. In the case of me showing you this with my laser and my diffraction gratings, the screen is the ceiling. It's where these dots are appearing. We have a light source. Does anybody know what monochromatic means? Other than single precise wavelength, because it says right there. Means one color. Monochromatic. So I have a red, well, I have a violet laser, or what else do we have to add here? Well, that's the double slit. This is often called Young's double slit experiment. The openings are very, very close together, and they're very tiny. So it's not like two openings that water waves are going to go through. These openings are microscopic. And in Physics 30, we would talk about how you manufacture these openings. Those are called bright spots, and they're antinodes. This is one of the reasons why we studied standing waves. An antinode is a region where there's a lot of energy. So where there's a lot of light energy is called an antinode. Those are the dark spots. And those are called nodes. Now there's a couple of other things that we have to add here, and I don't have them in this file. I ran out of time this morning. But I'm going to just put them off. Well, I'll put them on the diagram. This bright spot here is n equals 1. This bright spot is n equals 2. This bright spot is n equals 3. This is n equals 1. This is n equals 2. This is n equals 3. All right? It's the number that we use to describe which spot we're talking about. The central bright spot, I guess, sometimes it's called a central maximum, is n equals 0, but we will never use it in the formula. So you'll notice in both of those formulas at the top of the page, n is there, right? N is the number of the spot you're looking at. What x is this distance. It's the distance from the center to the spot you're talking about. But if that, I'm going to change this slightly. I'm going to go back to where I don't have all of this on here. So what we've said is this is n equals 1. You can just see this a little better. N equals 2, n equals 3. This is n equals 1. This is n equals 2. This is n equals 3. And I'm looking at what you're writing, and you have enough room to do that, right? Okay. And what I'm saying is this distance is x in the formula. But If you use that distance that I've just drawn as x, then you must put in n equals 2 in the formula. Okay? If you were to use, say, this distance as x, then what would you put in the formula for n? Nate? N equals 3. So n and x go together. N tells you which point you're talking about, so this would be n equals 3. N tells you which point you're talking about, and x tells you how far that point is away from the middle. By the way, what would the n value be for this dark spot? It's not a trick question, I don't think. 2.5, 2.5. It's kind of a linear scale. Even though it's not equally spaced, we would say that this is n equals 2.5. And that's called a node, a node, or a dark spot, or a minimum is sometimes the word you would see. L is the distance between the screen and the diffraction grating. And theta is the angle to that point that you're talking about. So I'm going to highlight something now for you. If you were in fact talking about this point, then that would be what you use for theta. So x is how far away from the center to the image you're talking about. And by the way, we typically draw this way, but when I show you this on the ceiling, the triangles are up there, right? X is the distance from the center of that vent to that dot on the left or the right of it. By the way, do you see that there are 3 dots to the left and 3 to the right? It's 3 together. If you look at where that speaker is, can you see there's actually 3 dots there? That's a defect in the diffraction grating. That's one image, okay? I think it's some kind of reflective interference pattern. So x is how far from the center to the image you're talking about. N refers to which image you're talking about. Theta is the angle to the image. L is the distance between the diffraction grating and the screen. Lambda is clearly the wavelength of the light. And D is how far apart the openings are. And I find that even if we ended there and you get to physics 30, you're not going to be totally lost. I mean, nobody should be totally lost if you make it through 20 and you do this in 30, but you will be much better off. So we're going to try to put this together now as a group and do a few examples. And as I said, if afterwards you choose to try some of the ones that are attached, feel free, but you don't have to. Calculate the angle of deviation, that would be theta, of the second order maximum. The second order maximum would be Alex, you're my assistant lately. Can you grab this? There's the button. You point it at the ceiling. Alex, can you point to the central maximum? Can you point to the n equals 1 maximum? Is there another n equals 1 maximum? Where's the n equals 2 maximum? Right there. So the angle to the n equals 2. You can hang on to that. We might need it again. That means we're trying to find theta. N is equal to 2. The diffraction grating has a d value of 5 times 10 to the negative 6 meters. Pretty small. And the wavelength of the light we're okay? Okay. And the wavelength of the light is 4.3 times 10 to the negative 7 meters. Well, we've got a formula that says lambda equals d sine theta over n. It's just a matter of putting these numbers in, isn't it? I'm going to rearrange this first. If I multiply both sides by n, I get this. Then I can divide both sides by d. It looks like all I have to do is take n lambda over d and take inverse sine, and I'll get the answer. N is 2 times the wavelength, which is 4.3 multiplied by 10 to the negative 7. By the way, that's violet light, 4.3 times 10 to the negative 7. And then divided by d, which was 5 times 10 to the negative 6. And take the inverse sine. Make sure you are in degree mode. About 10 degrees, 9.9 degrees. You get the same number? Okay. I'm going to kind of end it here. I want to give you a little bit of help, and I want to ask you, even though this is a physics 30 kind of idea, I do want to assign 2 problems, and the 2 problems you're going to do are the examples. Okay? Except, I have to show you something here. When you take a look at number 3, because you're going to be doing 2 and 3 for me. When you take a look at number 3, it says NM. That's not a typing mistake. You know what cm is? It's centimeters. NM is nanometers. And if you look on your formula sheet, nano is given to you as 10 to the negative 9. So when you enter 6 times 10 to the 2, which is 600 nanometers, you go 600 times 10 to the negative 9. The other thing I want to point out to you here in this question is, here's the central bright spot. There's the n equals 1, n equals 2, n equals 3, n equals 4. You're told that the distance between this point and this point is 0.12 meters. For reasons that I don't want to get into, in this question, those dots are evenly spaced. And that means that if they're evenly spaced, there's 3 spaces from here to here. 0.12 divided by 3 is 0.04. Can you take 0.04? So that means this is 0.04, this is 0.04, this is 0.04, this is 0.04. So you could use in this question x equals 0.04 and n equals 1. Could you use a different value for x? What could you use instead?
0.08.
And what would I use for n? 2. So I could use 0.08 and n equals 2. And just, I'll finish this off because, again, there are a couple of you that I think about these things. If the dots are equally spaced, that one formula that I said doesn't always work. If the dots are equally spaced, that formula works. Do you notice, however, that when I do this, that nothing happens? Do you notice that when I, there we go, do this, that these dots are, well, those ones pretty much are. There we go. Those dots are not equally spaced. They're getting further apart the further out you go. I think a red laser would be best. I was going to go, who took my red laser? There it is. There's a good example. If you look very carefully, the dots are getting further away from each other the further out you go, which means that that XD over NL formula wouldn't work, but you could use it here. All I'm asking you to do for homework is give these two examples a shot. Tomorrow we're going to look at reflection and refraction, and we're pretty much done the unit. There's a couple of loose ends we have to tie up on the day we get back, but your unit exam will be the Wednesday of the day we get back. So we're going to be reviewing on the Monday and the Tuesday after the break, and then write our exam. Okay? So not much time left, but that's okay. See if you can crack these two problems. I will, I'll post the answers in Google Classroom when I post the link to this video.